Hi, this is Liviu. With my colleague Shin, we are working on simulation research for evaluating the performances of the energy-efficient Ethernet-oriented network architectures and routing protocols. In this video, I will show you how we obtain the real traffic measurements and how we use them.
The Energy-Efficient Ethernet, or EEE, is a new IEEE standard approved on September 30, 2010. It uses a low-power idle mode instead of a continuous idle signal when there is no packet to transmit, for reducing the energy consumption of an Ethernet link. EEE adds an overhead to the packets, which is the time to wake the link from the low-power idle mode and the time to put it back to sleep. Packet coalescing groups individual Ethernet frames together and sends them back-to-back in a single burst. As a consequence, the relative overhead of EEE becomes smaller, leading to an increased bandwidth efficiency. EEE specifies a set of power-saving mechanisms but does not define where and when to use them. Such mechanisms depend on traffic demands, while the recent EEE studies consider only simplified Poisson traffic models. To better study the true potential and limitations of EEE, there is a clear need for real-world traffic measurements. Therefore, in this project, we measure the real traffic of a typical enterprise local area network through an aggregated port. We introduce our test bench network first, then we will present how we obtain the results and how to use them. INRS uses two separate fiber links with the outside world, one for the incoming and one for the outgoing traffic. Our measuring point is, however, equivalent to an optical network unit, ONU, in a passive optical network, PON. That's because the subscribers to a given ONU typically send and receive traffic over 100 megabits per second Ethernet links, while the ONU operates at 1 gigabits per second to send and receive data to and from the optical line terminal, OLT. Therefore, we consider that the measured traffic traces in this point can be used to simulate the performance of the EEE-enabled PONs.
So, here is the port where we measure the traffic, and here is the internal network of our organization.
Here we show you how we actually capture the traffic. The two 1 gigabit per second optical fibers transporting the incoming and outgoing traffic of the INRS organization are connected to a switch. From there, through a dedicated Ethernet cable, the whole traffic is collected by a 1 gigabit Ethernet PC card. Currently not connected. On the PC, we have to uncheck all the Ethernet adapter options to make sure the computer doesn't interfere with the traffic to be measured. In order to make sure that what we capture is representative, we first take a look of a wider statistics at the INRS traffic monitor, where the green lines represent the output and the blue lines represent the incoming traffic in bits per second. The monitor is at our internet provider end, so on the web page the labels are inverted in French. One can see in this picture at 1 day average that the measured period of time at the beginning of December 2010 is similar to the rest of the year, with weekend days having lower traffic. Zooming the last month, a 2 hours average here, one can see that there are similar daily patterns, with lower traffic during the night. For the last week, a 30 minutes average, the night and weekend particularities are even better emphasized. In order to preserve all those patterns, we decided to capture a whole week worth of traffic at microsecond precision or less, as limited by the operating system. In order to keep the size practical, we record only 5-minute trace files each hour, randomly to have a Monte Carlo-like sampling. In order to do that, we made a batch program, cap05min.bat, using the DAMCAP software from the Wireshark distribution. Once executed from the Wireshark folder, it should give these updates on the command line. For a week starting and finishing at 4 p.m. on Friday, so after work, from 3 to 10 December 2010, we obtain 168 PCAP trace files. To make these traces anonymous, we extract from them only the timestamps with microsecond precision and the length of the packet in bytes. In order to do that, we made a small batch program, conf2text.bat, using the T-Shark software from the Wireshark distribution. The text files obtained are then copied to another folder for further processing in MATLAB. For facilitating future traffic simulations using these traces, we extract only the relevant information and make them anonymous by relabeling the internal INRS computers instead of using their IP addresses. In order to do that, we use the MATLAB code prctraces.m, which builds first the list of the active internal computers. It checks the source computers list only based on the INRS IP masks. The destination computers list is irrelevant because there is a continuous external scanning of all internal IP addresses. We relabel then the 144 computers found and print out 168 text files for every 5-minute trace containing 4 columns. The starting timestamps of every packet in seconds from the beginning of the 5-minute capture, the packet length in bytes, the status as incoming 1 or outgoing 0 traffic, and the label of the internal computer. The names of the files include the date and time when the capture started, finishing with a label for our project. Following the link traces next to this webinar, an archive of all the capture traces can be downloaded from our website as a zip or RAR archive of less than 100 MB. In the prog subfolder are the programs used in this project in order to help you reproduce our experiment. Let's take an example and analyze the first packets of a trace in a graphical manner. Here is the time in milliseconds and the packet length in bytes. Every packet here. The capture always starts at the first arrived packet and finishes 300 seconds later. So the first packet, arriving at the timestamp 0, having 85 bytes or 680 bits, will last 0.68 microseconds, so less than 1 microsecond on a 1 gigabit transmission line. Then most of the 984 microseconds, or almost 1 millisecond, until the arrival of the next packet, is the idle period, which is the subject of our research. The timestamps during the idle mode are not explicitly mentioned in the traces in order to save space. Similarly, the second packet will last 1.12 microseconds, according to its length, while the rest of the 1.6 milliseconds is the idle period, and so on. The traffic measurements available on our website can be used for trace-driven simulations of the performances of EEE in real-world broadband access networks, such as Ethernet PONs and Ethernet local area networks. For example, in software test benches like OpNet, OmNet++, or NS2, one starts the simulation by making a random allocation of the 144 computers from our traces. Then, one generates packets according to their length, timestamp and direction, as provided in the traces, and implement the transmission between the corresponding computer and the OLT. The output will provide then real-time simulation results, like latency and jitter, or real-time results, like energy consumption or bandwidth utilization. That's all, folks. Please stay tuned for more webinars from our laboratory. www.zeitgeistlab.ca/technologies.html